So we're going to go ahead and actually try to end this section by taking a look at one other derivative rule, an important derivative rule here. Let's see what it says. Suppose that b is a positive real number constant. Okay, so b right here is just any number. Then how would I take the derivative of b to the power of x? So notice I'm talking here about like how would I take the derivative of something like 2 to the power of x? Notice that I can't use like the power rule here, because the power rule would have worked with things in the opposite order, where the power was a number. But what happens if my power is a variable? What do I do in that instance? Well, according to what we have up above in the box, we're told that if I'm ever taking the derivative of number to the power x, my answer should always just be the same number to that power of x times the natural log of that number. But the big question that we would have at this point is, why? How do I know that that's actually true? And so what we're going to do here is actually just try to quickly prove this result. Okay, to start, let's think about the function that we're going to want to take the derivative of, and I'll leave this piece here as just a little example of how this rule works. So let's suppose that we have a function y which is equal to b to the x. Well then, there's a lot of things that we could do with this function before taking its derivative. I could use a little bit of algebra first to rewrite this function. I'm going to do it in the following way. I'm going to rewrite this as e to the natural log of b to the x. And you might be thinking, Kyle, why in the world would you do this, and can you do that? But keep in mind that e to the natural log of something, since these are inverse functions, they're going to kind of, quote-unquote, cancel out, and you'll only be left with the input. You could try this on your calculator, right? Just type in something like e to the natural log of 7. The answer will be 7. So these guys are inverse functions. They undo each other. And so these two statements here are actually completely equivalent. But the reason that I'm actually going to do this is because now I can make use of a nice little property of logarithms that we talked about in the skills check. Specifically, the power rule for logarithms, which states that I can take this exponent of x and I can actually bring it down to the front of that natural log, like this. Now, once I have this, I'm going to go ahead and attempt to calculate my derivative. So I'm going to say that instead of taking the derivative of y equals b to the x, I'm going to take the derivative of y equals e to the x times natural log of b. This is, again, completely equivalent to what we started with, but it's in a slightly different shape, and so I think I should be able to tackle it. Notice that what I have up here is just e raised to a power, and in that power, what I actually have is x times the natural log of a number, but that's really just going to look like e to the number times x, maybe like e to the 3x or e to the 2x or e to the pi x, right? I mean, it could just be e to some number times x. So when taking its derivative, this is actually going to be really, really simple. I'm going to notice that when I do the derivative of e to the stuff, by the chain rule, I would just get e to the stuff. But then I would look at the stuff, and I would have to recognize that it's not just an x, and so I would need its derivative. But since this is just a number times x, this is like taking the derivative again of like x times 3 or x times 2.7, right? It's just going to end up being the constant as popping out of that derivative. So my result here is actually just going to look like e to the x times the natural log of b times natural log of b. And with a little bit more algebraic reworking, I can see that I could take this value of x and bring it back up as a power now. So I could write this as e to the natural log of b to the x. I could do that again. And the reason that that's advantageous is that now my e and my natural log will undo each other, and I will be left with a value of b to the x times the natural log of b. And so this here is indeed the derivative formula, just as stated up in the box above. And again, how that actually works or plays itself out is shown right here in an example like this. If I was doing a derivative of 2 to the power of x, I would just do 2 to the power times the natural log of 2. So this is another rule here, and actually on the formula sheet, you'll see that it falls directly under this chain rule that we have listed here. And here's my derivative for exponential functions. Derivative of b to the x is b to the x times natural log of b. Now what's really cool about this is that this rule actually implies a rule that we've already known for quite some time now, that the derivative of e to the x is just e to the x. Notice that if we replaced the value of b with the number e, we would get that the derivative of e to the x is e to the x times natural log of e. But what's the natural log of e? The natural log of e is just 1. So if b is replaced with e, the derivative would be e to the x times 1, or just e to the x. So this is actually completely consistent with everything that we've already known about our derivative of e to the x. Now this is a really important rule to memorize. It's one that's very often forgotten by a lot of calculus students, and so it's one that you might want to, in particular, try to dedicate to memory, since it tends to be one of the harder ones to remember.